Very good evening to all of you. So today we will try to understand the Class C power amplifier. Now we have already studied the Class A, Class B power amplifier and Class AB power amplifier. Now to understand the differentiation between these amplifier, you will have to take the output characteristics of the common emitter configuration. We know that the common emitter configuration is normally used for the amplification purpose. So by just looking at the output waveform, what you can see that the when the operating point is at the middle of the DC load line, then that amplifier is called the Class A power amplifier. When your operating point is at the boundary of cutoff or it is near to the saturation, then that operating point, then that power amplifier is called the Class B power amplifier. Now, similarly, if you put your operating point just above the cutoff or slightly below the saturation, then that is termed as the Class AB power amplifier. And when your operating point is in a deep cutoff, so we can say that power amplifier is the Class C power amplifier. As you know, the efficiency of the Class A power amplifier is around 25%. Now, if we switch towards the transformer coupled, that was directly coupled. And if you switch to the transformer coupled, then your efficiency will be enhanced by 50%. So what we can see here, Class A amplifier is having an efficiency of 25%. Class B will be having the efficiency of around 78.5%. And suppose if you want to enhance the efficiency more, then you need to go for the next power amplifier, that is the Class C power amplifier. So normally this amplifier is used only when high efficiency are required. So you can see in the advantage, the efficiency of this amplifier is around 90%. Now, this is the simple circuit diagram of the Class C power amplifier. You know that your point is in the deep cutoff. So when your point is in the deep cutoff, so what is going to happen? Normally, we will always place our AC signal on to the DC operating point. So in that case, your AC will get amplified. Now, where is your operating point? Your operating point is in the deep cutoff. So what is going to happen? I am going to place my AC signal. So you can see that only a some part of this signal is in the active region, and the remaining part is in the deep cutoff. So that is not going to contribute into your output signal. Only this small part will be available at the output. As this part is in the active region, so this will only go for the amplification. Rest part is in the cutoff, and the signal which is in the cutoff will not go for the amplification. So what you can see that if your signal is AC input signal, then you will be having only a part of that signal, and this will go to the load. So this is called the Class C power amplifier. Now looking at the circuit diagram, you can see here, as you know that our operating point is not at the middle, so you don't require any biasing circuit. And but you need to place your operating point in the deep cutoff. It means that you need to push your signal in that region. So for that, a pull-up resistor is connected. Now this is the pull-up resistor. So this will pull your operating point below the cutoff. So just to take a transistor and across the base and emitter terminal, you will have to connect the base resistor, and this base resistor is going to pull your operating point below the cutoff, because we want only a part of input signal to be amplified. We don't want the entire signal to be amplified. If you want the entire signal, then you need to go for this Class A amplifier. And if you want the half of it, then you need to go for the Class B power amplifier. And the Class class B power amplifier, you will be requiring two complementary transistor or the symmetrical transistors. So this is very simple. You take one transistor and you connect a resistor, that is the base resistor, across base and the emitter terminals, and to this you will have to apply the input signal. Now, as you can see that there is a parallel resonance circuit. So before using that resonance circuit, that is a parallel resonance circuit, you will have to understand the concept of it. Now, as you can see that both are energy storage elements. Basically, we are having three passive elements, and among these three passive elements, the resistor is the energy dissipating element, and inductor and the capacitor are energy storing elements. So they are going to store the energy and they will transfer the energy onto each other. So we'll take a simple series resonance circuit. You can see here I am taking the value of L, then this is the capacitor. So what will happen at the resonance condition? You can see that the inductive impedance will be equals to capacitive reactance. Normally we learned this thing in our lower classes, that in the resonant condition, or you can see at the resonance condition, your XL will be equals to XC. So XL means what? That is omega into L, and XC will be equals to 1 upon omega C. Now, putting this value here, so omega square will be equals to 1 upon LC. We want omega, so that one will be 1 upon under root of LC. This is the angular frequency. If you want to be in the linear frequency, so that will be 2 pi into f, 1 upon under root LC. So f will be equals to 1 upon 2 pi into under root of LC. So this is the resonant frequency, and normally this frequency is higher than the power frequency. Now, what is the power frequency? Power frequency is around 50 hertz, and this frequency is in the kilohertz region. So normally the class C power amplifier, suppose if you are using this resonance circuit in our class C power amplifier, so this power amplifier will be used for the radio frequency. Radio frequency means above your audio frequency range, and audio frequency range is from 20 hertz to 20 kilohertz. So normally this class C power amplifier is used for the frequencies above 20 kilohertz. So we can say it is used uh, for radio frequency application. So this is about the series resonance circuit. So what is going to happen now? If you want to calculate the effective impedance, so effective impedance will be equals to what? That is J into XL. I'll rub this portion because we have got the resonant frequency. Now, if you just put down the values, you select the values, you are going to get the resonant frequency. So, this is JXL, and then plus minus J into XC at a resonant frequency, at the resonant frequency. So what is going to happen? These two values are equal. So what you can see that XL will be at resonant frequency, XL will be equals to XC. So this is minus J into XL. If you yeah, if you substitute the impedances, so this is 0. So in a series resonance circuit, what is going to happen? You will be having a short circuit. You will be having a short circuit. This will be resembled to this short circuit at only resonant frequency. Fine, at only resonant frequency, or you can just understand the concept from the curve also. We will take the impedance versus frequency curve. This is the frequency. We are increasing our frequency from the DC value, that is 0 hertz, to the some higher value. Now you can see that XL will be equals to what? 2 pi f into L. So when you are keeping the inductance constant, normally the once you design your inductor, so your inductance will be constant. So in that case, your XL is directly proportional to your frequency. So this will be having a linear relationship. Now, similarly, Xc will be equals to 1 upon 2 pi f into C. So they are having the inverse relationship. So Xc will be 1 upon f. So if you are going to plot the curve like this, right? So you can see here at this point, your two curves are intersecting, or you can say bisecting. So that frequency is called the resonant frequency. This frequency is called the resonant frequency. It's a simple concept. So at the resonant frequency, your series resonant circuit will look like a short circuit. Just you need to imagine that this will just resemble like the closed wire, like you have like your switch is closed. Now similarly, coming here at the parallel resonant circuit, which we are using it for our class C power amplifier, this one will be L and this. Now, if you want to calculate the net, you can say impedance or the reactance. So what will be, this is the parallel combination. So in that case, this one will be J into XL minus J into XC. And this is JXL minus J into XC. Now at a resonant frequency, as a resonant frequency, this XL will be equal to XC. So what is going to happen? JXL minus JXC. So you can see that this is a numerator value. I think numerator value, just root, and this will be 0. So I think the infinity is going to come. So what is going to happen? This parallel resonant circuit at resonant frequency will resemble like an open circuit. So when this frequency is going to arrive at your in your system, then your system will become an open circuit, or you can see that the switch has opened. So this is a simple concept which we are using it for our class C power amplifier. Now you can see here, normally we measure the output at the collector. Fine, the collector to emitter we can say. So normally we put our tapping here at the collector, and above that there is a parallel resonant circuit. So when you are applying an input signal at radio frequency, normally we assume that the resonant frequency for this parallel resonant circuit is a radio frequency which is about 20 kilohertz. So when that frequency is going to arrive, then this one will become an open circuit. So there will be no power dissipation. There will be no power dissipation. Normally, the main cause of the reduction in the efficiency is the DC voltage, or you can say a biasing voltage. So this is not coming into the picture when the radio frequency is applied. So this circuit will be having the highest efficiency because you have connected the parallel resonance circuit, and your parallel resonance circuit will be acting as an open circuit at only resonant frequency, which in our case we have taken as the radio frequency. So this is about the class C power amplifier operation. Now we will take the drawbacks of it. Now what is the drawback? Now this circuit is not going to be activated for the audio frequency. So audio frequency for this circuit is not going to be applicable. But and at the same time you can see there is a non-linearity. Non-linearity because you are going to amplify only a part of it. Only a part of it will be amplified. So that will introduce a non-linearity into your system. Fine. So you can see here only a part of it will be amplified, and the rest remaining part will not be amplified because this part has entered into the cutoff region. And why it has entered into the cutoff region? Because RB is pulling your operating point in deep cutoff, and because of that, that remaining part will be cut off, or you can say clipped off. This is all about the classic power amplifier. So in the next video, we'll try to understand some numericals on the power amplifier. Thanks a lot.